I'm going to go through very briefly how to do some molarity calculations with you. So let's get started right away. So here's our first question. How many moles of solute, remember solute is what is being dissolved, are required to make 1.35 liters of a 2.5 molar solution? Because this involves moles and molarity and volume, we're going to use this little mnemonic right here. And what it says is if you cover up, this stands for M, big M, molarity, moles, and liters. If we were to cover up molarity, molarity would be equal to moles divided by liters. Moles divided by liters. If you were to cover up liters, liters or volume would be equal to moles divided by molarity. And then finally, if you're trying to solve for moles, moles would be equal to molarity times volume. So in this case, that's what we want to do. So moles is molarity times volume. We're given the volume of 1.35 liters, and the molarity is 2.5 molar. So we can directly plug those into the equation. Now, the unit for molarity is moles divided by liters. When you multiply that by liters, the liter cancels and you'll be left with moles. Typing this into my calculator, I get an answer of 3.38 moles of solute would be needed to make a 2.5 molar solution and a volume of 1.35 liters. Now, what if the question had instead stated, what mass of sodium hydroxide is required to make 1.35 liters of a 2.5 molar solution? I would basically have to do this first step just the same. But now really what I'm asking is, well, how much does 3.38 moles of sodium hydroxide weigh? And to answer this, I will set up a dimensional analysis question. So my question says, how many grams of sodium hydroxide is equal to 3.38 moles of sodium hydroxide? I need to figure out the molar mass of sodium hydroxide. I know that 1 mole of sodium weighs 23 grams, 1 mole of oxygen weighs 16 grams, and 1 mole of hydrogen weighs 1 gram. So therefore, sodium hydroxide weighs 40 grams per mole. So I'm going to put that in. 1 mole of sodium hydroxide has a mass of 40 grams. Moles of sodium hydroxide cancel, like that. And now I simply have to take 3.38 times 40, and I get my answer, 135 grams of sodium hydroxide. So what that says is, if I want to make 1.35 liters of a 2.5 molar sodium hydroxide solution, I will need to mass out 135 grams of sodium hydroxide and then dissolve that in solution to bring the volume up to 1.35 liters. Pretty easy. Let's try another example. This time, let's pretend the question said, what mass of magnesium phosphate is required to make 1.35 liters of a 2.5 molar solution? I'm going to use the same process we just went through. So I'm going to set up my dimensional analysis. How many grams of magnesium phosphate, be sure you have the right formula, is equal to 3.38 moles of magnesium phosphate. Now I have to figure out the molar mass of magnesium phosphate. Well, looking at this formula, I have 3 magnesiums, each that weigh 24 grams per mole, 2 phosphorus that each weigh 31 grams per mole, and 8 oxygens, each weighing 16 grams per mole. So that gives me a pretty large number. That says 1 mole of magnesium phosphate is 262.9 grams. Notice the moles of magnesium phosphate cancel like that. And when I type this in my calculator, 3.38 moles times 262.9 grams, I get my answer, 889 grams of magnesium phosphate. Now, some of you might be wondering, why do you get 2 different answers, 2 different masses, even though we're making the same volume with the same concentration? Well, the answer is quite simple. These 2 materials, sodium hydroxide and magnesium phosphate, have a different molar mass. And because they have a different molar mass, it requires different amounts of those different masses. Hope that makes sense. Let's try another problem. So this question says, let's find the molarity of 58.6 grams of barium hydroxide in a 5.65 liter solution. Now, if you remember the equation earlier, we said that you have to have molarity is moles over liters. Right now, I have grams, so I need to convert that into moles. That's my first step. So let's figure out how many moles of barium hydroxide this is. Barium is an alkaline earth metal with a +2 charge. Hydroxide has a 1- charge, so the formula for barium hydroxide is BaOH2. So let's figure out how many moles is equal to this many grams. So now I need to figure out the molar mass of barium hydroxide. I'm going from memory, but I believe barium is about 137 grams per mole. I have 2 oxygens at 16 each, is another 32, plus 2 hydrogens, 2 more grams. So if we've done the math right, that's about 1 mole of barium hydroxide, 171.3 grams of barium hydroxide. At this point, grams of barium hydroxide cancel, like that. And if I take the 58.6 grams divided by 171.3, it turns out we have 0.342 moles of barium hydroxide. So even though this question is a little bit more work for that first step, it gets us to the point of going from grams to moles. And now, of course, we're trying to get to molarity. We remember molarity is moles, which I just calculated, divided by volume. So let's do step 2. So we want to figure out what is the molarity of a 5.65 liter solution that has this number of moles of solute. So using our mnemonic from the previous page, we know that molarity is moles over liters. I'm given, or I figured out the number of moles, and I was given the volume, so I can substitute this in. For moles, I'm going to put in the 0.342, and for the volume, 5.65. Now, when I solve that on my calculator, I get the answer, and the answer is 0.061 molar barium hydroxide. I'm not too worried about sig figs here. There's probably another digit needed there, but I'm not too concerned about that, nor should you be. Let's see what comes up next. Well, this is a shortcut way we could have solved it to figure out what's the molarity. It's moles, that's all the stuff on top, divided by volume. If I had the mass, I know that 1 mole is 171.3 grams. The grams cancel, and I'm left with moles divided by liters. I get the same answer. This is a little bit bulky, a little bit cumbersome. I would prefer to break the problem into 2 steps if I were personally solving it. But if you'd like to do it the way I've shown on the bottom, that's fine as well. Let's try another problem. Now, this one is not molarity. It's another way to measure concentration, but I'll just put it out there for fun. It says, what mass of calcium fluoride must be added to 1,000 liters of water so that the fluoride atoms present are going to be at a concentration of 1.5 parts per million. Now, this might be important for a city's water municipal department to figure out how much fluoride to add to water. Fluoride hardens your teeth and makes them a little bit less susceptible to cavities. So here's how we could solve this problem. We need to figure out, well, how many molecules of water are there in 1,000 liters? Now we can do some conversions. We know that 1 liter is 1,000 milliliters, and the volume of liter cancels. And then we know that 1 milliliter of water has a density of 1 gram. That's the density of water. And then finally, we know that for every 18 grams of water, that's 1 mole of water. Now, if I stop here, I'll be left with moles, and what I really want is molecules. So I need one more step. For every mole of water, there are 6.02 times 10 to the 23rd molecules of water. Going through the math there, 1,000 liters of water is equal to approximately 3.34 times 10 to the 28th molecules of water. Now at this point, I'm simply setting up a ratio. I want to know how many atoms of fluorine do I need for 3.34 times 10 to the 28th molecules, and what I know that it needs to be equal to is 1.5 atoms per million molecules of water. Now, if I was technically correct, I'd write 1.5 atoms on top, and I'd write 999,998.5 molecules, and the other 1.5 would be fluorine. But this is close enough. At this point, I'm going to cross multiply. So I take 1,000,000 times x equal 1.5 times 3.34 times 10 to the 28th. So I'm cross multiplying and dividing. And what I get for x is 5.01 times 10 to the 22nd atoms of fluorine. Now I know how many atoms I need. Where do those atoms come from? Well, they come from calcium fluoride. And remember, the original question was asking, what mass of calcium fluoride do I need? So to continue, we know that if we multiply this, there are 2 atoms of fluorine per molecule of calcium fluoride. So atoms of fluorine will cancel, and I'll be left with a certain number of molecules of calcium fluoride. This is how many molecules I need. I'm almost done with the problem. I now just want to figure out how much that would weigh. So we'll do a little bit more dimensional analysis. To go from molecules to moles, I'm going to use Avogadro's number. Every 6.02 times 10 to the 23rd molecules of calcium fluoride are equal to 1 mole of calcium fluoride, and molecules cancel. Finally, I just have to figure out what this weighs. Well, the molar mass of calcium is approximately 40, and each fluorine is 19 times 2, so that's 38. So about 78 grams per mole is the molar mass of calcium fluoride. Moles of calcium fluoride cancel, and I finally got my answer that I'm looking for. It's going to take about 3.25 grams of calcium fluoride dissolved in 1,000 liters of water, and that should yield a concentration of fluoride in the water of 1.5 parts per million. Now, I won't ask you any questions like this, but this is a question that, again, a water municipality might need to figure out how to do. And so it's just a fun, brainy little project to figure out and do ourselves. Let's see. How about we stop there? Yep, I'm going to stop right there for you. And if I hit that button, we'll say goodbye. Take care.